Route array s power n a0 a2 a4 s power n minus 1 a1 a3 a5 s power n minus 2 a1 a2 minus a0 a3 by a1 a1 a4 minus a0 a5 by a1 a1 a2 a1 a2 minus a0 a3 by a1 a1 a4 minus a0 a5 by a1 a1 a4 minus a0 a5 by a1 s power 0 a and so on and an. For closed loop system to be stable, all the coefficients in the first column must be positive and there should not be any missing coefficients in the first column. If there is any sign changes in the first column of the row array, then system is unstable. Number of sign changes is equal to number of roots lying in the right side of the S-plane. Magnitude and sign of every term in each row and column depend on first column element. Therefore, we always see first column term. The presence of a zero in the first column of the row tabulation leads to following conclusions. Equal real roots with opposite signs, pair of conjugate roots on imaginary axis. Difficulties and limitations of row array. The row array is applicable to LTI system only. It determines the poles in LHS or RHS of S-plane but not their exact location. Whenever any one coefficient is 0 in first column, then replace 0 by smallest positive constant epsilon and continue the row arrow. Finally, substitute epsilon equal to 0 and check for the sign change. When row theory ends abruptly, construct an auxiliary equation and differentiate it, get new coefficient to complete the row array. When the system is marginally stable, find the frequency of sustained oscillations from auxiliary equation. The auxiliary equation should be an even polynomial or order 2 only. Root locus. Root locus is defined as the locus of closed loop poles obtained when system gain k is varied from 0 to infinite. Angle condition is used for checking whether certain points lie on root locus or not, and hence the validity of root locus are for closed loop poles. For a point to lie on root locus, the angle evaluated at that point must be on odd multiple of plus or minus 180 degrees, that is plus or minus 2q plus 1 into 180 degrees. Magnitude condition. The magnitude condition used for finding the system gain k at any point on the root locus. Modulus of g of s h of s equal to 1. Construction rules of root locus. Root locus is symmetrical about real axis. Let p equal to number of open loop poles, z equal to number of open loop zeros. If p greater than z, the number of branches of root locus equal to p. The number of branches terminating at 0 equal to z. The number of branches terminating at infinite equal to p minus z. A point on real axis is said to be on the root locus if to the right side of this point the sum of number of open loop poles and zeros is an odd number. Angle of asymptotes. Number of asymptotes equal to p minus z. Number of angle of asymptotes equal to 2q plus 1 into 180 degrees by p minus z, where q equals 0, 1, 2 and so on. Centroid is the point of intersection of asymptotes on the real axis. Centroid equal to the sigma real part of open loop poles minus sigma real part of open loop zeros by p minus z. Breakover point. They are the points where multiple roots of characteristic equation occurs. Proceed to find out breakover point. Construct characteristic equation, that is 1 plus g of s h of s equal to 0. Where k in terms of s, find dk by ds. The root of dk by ds equals 0. Give breakaway points. Intersection of root locus with imaginary axis. Roots of auxiliary equation at k equal to k marginal from root array gives intersection of root locus with imaginary axis. The angle of departure and arrival. The angle of departure is tangent to the root locus at the complex poles phi d equal to 180 degrees plus phi. The angle of arrival is tangent to the root locus at the complex 0. Phi a equal to 180 degrees minus phi equal to phi z minus phi p, where phi z equals sum of angles subtended by remaining zeros. Phi p equals sum of all angles subtended by the poles. Whenever the system transfer function consists of the poles at origin, then the root locus is nothing but angle of asymptotes. Value of system k on root locus can be found out by k equal to pi into phasor length from open loop poles by pi into phasor length from open loop zeros. Effect of addition of pole. Operating range of k decreases for system to be stable. Relative system stability reduces. System becomes more oscillatory. The breakaway point shift towards the imaginary axis. Damping factor decreases and system becomes unstable. Settling time Ts and bandwidth increases. Real time Ts decreases. Real time rise time DR decreases. Effect of addition of zero. System becomes stable. Relative stability improves. Range of K for stability increases. System becomes less oscillatory. Breakaway points shift towards the left side of the S plane. Damping factor increases. Bandwidth decreases. Controller it is a device that is used usually in series with a plan to drive the plan towards decreased output. Types of industrial controller: proportional controller, RS, KP, omega n square by S plus omega n square by S into S plus 2 zeta omega n S. Omega n dash equal to omega n into root KP. Zeta dash equal to zeta by root KP. Where Kp is proportional constant. Effect: natural frequency of oscillation omega n increases by root Kp. Damping ratio zeta decreases by root Kp. Peak overshoot MP increases. Steady state error reduces. Derivative controller SKD omega n square by S into S plus 2 zeta omega n, where KD is rate constant. Type and order of the system reduces by 1. Oscillations dies out, hence transient response improves. Not used in oscillations. Not used in oscillations. Integral control K1 by S omega n square by S into S plus 2 zeta omega n, where Ki means integral scaling. Integral controller is a memory based controller. The effect increases with type and order by 1, makes the system less stable. Steady state error reduces. It improves the steady state response. PD controller. PD means P and D controller. KP parallel with KDS in series with omega n square by S square S into S plus 2 zeta omega n. Transient response improves. Damping ratio increases. Peak offset decreases. Bandwidth increases. Noise level increases. Improves gain margin, phase margin, and resonant peak. PI controller KP KI by S omega n square by S into S plus 2 zeta omega n S అలాగే ఉంటుంది. Improves steady state response, improves type and order of system by 1, noise level reduces, increases error constant, bandwidth reduces. PID controller parallel of SKD KP KI by S, okay na, in series with omega n square by S into S plus 2 zeta omega naught. It is similar to lead lag compensator and bandwidth reject filter. PID control is nothing but similar to lead lag compensator and band reject filter. Effect improves both steady state as well as transient response, reduces rise time, it increases bandwidth, it increases stability, it eliminates steady state error between input and output, it increases type and order of system by 1. Compensator. Introduction. Compensator and control systems are used for improving the performance specifications, that is the transient and steady state response characteristics. Lead compensator V naught of S by Vi of S equal to alpha into 1 plus tau S by 1 plus alpha Ts, where T equal to R1C and alpha equal to R2 by R1 plus R2. Circuit is R1 parallel with 1 by SC. Okay, na? And parallel with R2, output is taken to R2 V naught of S. 0 is close to origin and the port. It is similar to the PD controller. Effect of lead compensator. It improves the transient response, increases the margin of stability, it increases the bandwidth, signal by noise. Output is less than signal by noise input. It helps to increase error constant up to some extent. It all allows to pass high frequencies and it mutes low frequencies. Increases the phase shift. Lag compensator R1 అడ్డగా వచ్చేసింది R2 1 by CS. అవుట్పుట్ V naught of S R2 1 by CS దగ్గర అవుట్పుట్ V naught of S తీసుకుంటాం. V naught of S equal to 1 plus TS by 1 plus beta TS. T equal to R2C and beta equal to 1 by alpha equal to R1 plus R2 by R2, beta greater than 1. Pole is close to horizon than the 0. It is similar to the PI controller. Effect of lag compensator. It improves the steady state response, increases the error constant, decreases the bandwidth, it reduces the effect of noise, reduces stability margin, does not affect the transient response. System becomes less stable. It allows to pass low pass frequencies, attenuates the high frequencies, decreases the phase shift. Lead lag or lag lead compensator. R1 parallel with 1 by C1s. R2 series to 1 by C2s. R2 1 by C2s దగ్గర అవుట్పుట్ V0 of S తీసుకుంటాం. V0 of S equal to alpha into 1 plus T1s into 1 plus T2s whole by 1 plus alpha T1s into 1 plus beta T2s. T1 equal to R1 C1, T2 equal to R2 C2, alpha equal to R2 2 by R1 plus R2, and beta equal to R1 plus R2 by R2. The effect of lead lag or lag lead compensator. Lead lag network improves both steady state and transient response of the system. Note, compensator in the form of G of S equal to S plus C by S plus B will work as lead compensator if A less than B and as lag compensator if A greater than B. Frequency at which maximum phase occurs is omega root AB radians per second. Maximum phase phi m is given as sin phi m equal to 1 minus alpha by 1 plus alpha, where alpha equal to A by B. Frequency response analysis. Frequency response analysis for second order system transfer functions E of S by R of S equal to omega n square by S square plus 2 zeta omega ns plus omega n square. Resonant frequency, it is defined as the frequency at which the magnitude has maximum value. Omega r equal to omega n into root over 1 minus 2 zeta square. Omega r equal to omega n into root over 1 minus 2 zeta square. Resonant peak, it is maximum value of magnitude occurring at resonant frequency omega r. Mr equal to 1 by 2 zeta into root of 1 minus zeta square. Phase angle at resonant frequency phi equal to tan inverse half root over 1 minus 2 zeta square by zeta. Phi r equal to minus tan inverse half root over 1 minus 2 zeta square by zeta. Remember, as zeta approaches 0, omega r approaches omega n, and mr approaches to infinite. As zeta less than 0 to less than zeta less than or equal to 1 by root 2, the resonant frequency always has a less value than omega n, and the resonant peak frequency, the resonant peak has a value greater than 1. Cutoff frequency bandwidth. Cutoff frequency omega c equal to omega n into 1 minus 2 zeta square plus root over 4 zeta power 4 minus 4 zeta square plus 2 whole over 1 by 2. Bandwidth equal to omega c. Stability from frequency response part phase margin pm equal to 180 degrees plus angle of g of h of omega, g of j omega, h of j omega at the gain crossover frequency. Gain margin gm equal to 1 by modulus of g of j omega, h of j omega to omega equal to omega bc equal to 1 by x. That phase crossover frequency gm in dB equal to 20 log 1 by x. Remember, for stable systems, gain crossover frequency less than phase crossover frequency. Gain margin, phase margin both are positive. For unstable systems, gain crossover frequency greater than phase crossover frequency. GM and PM are both are negative. For marginal stable systems, gain crossover frequency equal to phase crossover frequency. GM and PM both are 0. GM and PM for second order systems. Gain crossover frequency omega gc equal to omega n into root over minus 2 zeta square plus root over 4 zeta power 4 plus 1. Phase margin pm equal to tan inverse of 2 zeta by root over minus 2 zeta square plus root over 4 zeta power 4 plus 1, that equal to 100 zeta. Gain margin is first and second order systems is infinite. Polar plot. It is a plot of absolute values of magnitude and phase angle in degree of open loop transfer function g of j omega h of j omega versus omega drawn on polar coordinates. General shapes of polar plot type 0 order 1 g of s equal to 1 by ts 1 by 1 plus ts. అదేమొస్తుంది కింద నుంచి ఇలా వస్తుంది. Type 0 order 2 g of s equal to 1 by 1 plus ts into 1 plus t2s. అదేమంటే ఫస్ట్ క్వాడ్రంట్ టు సెకండ్ క్వాడ్రంట్ కింద నుంచి వస్తుంది. సారీ, థర్డ్ టు ఫోర్త్ క్వాడ్రంట్ కింద నుంచి వస్తుంది. ఒమేగా ఈక్వల్ 0 ఒమేగా ఈక్వల్ 20. Type 0 order 3 g of s equal to 1 by 1 plus t1s 1 plus t2s 1 plus t3s. అదేమవుతుందంటే ఫోర్త్ థర్డ్ సెకండ్ తిరుగుతూ ఉంటుంది. టైప్ 4 ఫోర్త్ థర్డ్ సెకండ్ ఫస్ట్. టైప్ 1 ఆర్డర్ 1 g of s equal to 1 by s negative weather axis. Order 2 quadrant 3 order 3 quadrant 3 and 2 Order 4, g of s equal 1 by s into 1 plus t1s into 1 plus t2s into 1 plus t3s is nothing but omega equal to 0 నుంచి ఇన్ఫినిటీ పోతే 3 to 1 like that. For standard transfer function of type 2 and type 3 systems, the polar point not instructions negative real axis as many times as there are zeros in open loop transfer function. Nyquist stability criteria. Nyquist stability criteria states that the number of encirclements about the critical point minus 1 plus j0 should be equal to poles of open loop transfer function g of s h of s, which are in the right half of s plane, that is n equal to p minus z. For stability, z equal to 0, n equal to p, where capital P equal to number of open loop poles in RHS of S plane, Z equal to number of closed loop poles in RHS of S plane, N equal to number of encirclements of about of the point minus 1 plus J0 by G of S H of S plot, the positive direction of encirclements being anticlockwise. Bode plot, the variation of magnitude and sinusoidal transfer function expressed in decibel, the corresponding phase angle in degrees being plotted with respect to frequency on a logarithmic scale in rectangular axis. The plot thus obtained is known as Bode plot. Procedure to draw Bode plot: S is replaced by j omega to convert into frequency domain. Find magnitude in terms of omega and write in terms of dB. Magnitude in dB, mdB equal to 20 log of g of j omega h of j omega. Find the phase angle of phi equal to inverse half imaginary part by real part with required approximation, and by varying the frequency from minimum to maximum, draw the magnitude and phase plot. G of s h of s equal to k, mdb equal to 20 log k. System gain k, shift the magnitude plot either upward or downward by 20 log k. Slope equal dm db by d log omega. The magnitude plot should start at the frequency of 0.1 with opposite sign of the slope, and it should pass through 0 dB line and intersect at omega equal to 1 and k equal to 1. N poles at origin gives slope equal to minus 20 n dB per decade, angle phi equal to minus 90 degrees n degrees. N zeros at origin gives slope equal to plus 20 n dB per decade, angle phi equal to plus 90 degrees 90 n degrees. Remember, the initial slope of the magnitude plot is given by the poles or zeros located at origin. Corner frequency, the frequency at which slope changes from one level to another level. G of s h of s equal to 1 by 1 plus h tau whole power n. Frequency below corner frequency slope is 0, phase of phi equal to 0. Above corner frequency minus 20 n dB per decade, phase phi equal to minus 90 degrees n. G of s h of s equal to 1 plus s tau whole power n. Frequency below corner frequency slope is 0, phase is 0. Above corner frequency 20 n dB per decade degrees in degrees. The error is nothing but difference between actual value and asymptotic value. Error is maximum at corner frequency. Error is even function with respect to corner frequency. 6 dB per octet equal to 20 dB per decade. 6 dB per octet equal to 20 dB per decade. Classification of systems. Minimum phase systems, MPS, a system in which all finite poles and finite zeros are located in left half of S plane, then it is called as minimum phase system. Non-minimum phase systems, NMPS, a system in which one or more zeros lies in the right half of S plane, remaining all the poles and zeros lies on the left half of S plane. All path systems, a system in which zeros lies on the right half of S plane, poles lies on the left half of S plane, and which are symmetrical about imaginary axis. For all path systems, magnitude should be 1 and phase angle is minus 180 degrees. Gain NMPS equal to gain MPS into gain APS. Angle of phi NMPS equal to angle of phi MPS plus angle of phi APS. Constant magnitude velocity, M circles representing magnitude of closed loop frequency response plotted against frequency. Radius of M circles, radius equal to M by 1 minus M square. Center of M circle, center equal to M square by 1 minus M square comma 0. Constant phase angle loci, N circles represents phase of closed loop frequency response plotted against frequency. Radius of N circles, radius equal to root over 1 by 4 plus root over 1 by 4 plus 1 by 4 n square. Center equal to minus 1 by 2 comma 1 by 2 n equal to tan phi. State space analysis. State describes the future behavior of system based on present and past data. Knowledge of present is given by input, knowledge of past is given by state variables. State variables, these are the minimum set of variables such that the knowledge of these variables along with the input can completely describe behavior of the system. State space, the set of possible values that is states vector can assume is called state space. General representation of state model, state equation x dot equal to ax plus bu, output y equal to cx plus du, x dot equal velocity vector n into 1, x is state vector n by 1, u is input vector m by 1, y is output vector p by 1, a equals state matrix n by 1, b equal input matrix n by m, c is nothing output matrix p by n, d transmission matrix p by m, n number of state variables, p number of outputs, m number of inputs. Controllability. A system is said to be controllable if it is possible to transform the initial state of the system to any desired state with application of input within a finite interval of time. QC equal to B, AB, A square B, and so on A per n minus 1 B. Where QC is nothing but controllability test matrix. Condition for state controllability, QC is not equal to 0. Matrix be non-singular. Observability, system is said to be observable. If it is possible to measure at state variables by measuring the output, Q not equal to C, Q not equal to C transpose, A transpose, C transpose, A transpose whole square, C transpose, and so on, A transpose whole per n minus 1 C transpose. Where Q naught observation test matrix condition for state observability, modulus of Q naught is not equal to 0. Matrix to be non-singular. If AB is controllable, A transpose B transpose is observable. If AC is observable, A transpose C transpose is controllable. If AB is controllable, A transpose B transpose is observable. If AC is observable, A transpose C transpose is controllable. If input output transfer function for a linear time invariant system does not have any pole zero cancellation, the system can always be represented by completely controllable and observable state models. Transfer function T of C into Si minus a whole inverse into B plus T. State transition matrix E power A t equal phi of t equal Laplace inverse of Si minus a whole inverse. Properties of STN, phi of 0 equal to I, identity matrix, phi inverse of t equal to phi minus t, phi of t whole power k equal to phi of kt, phi of t1 plus t2 equal to phi of t1 and phi of t2, phi of t2 minus t2 equal to phi of t minus t1 minus t naught equal to phi of t2 minus t naught.